Welcome to the Out of Bounds Read podcast, where we help inform and grow the community around common weakness enumeration and common attack pattern enumeration and classification. This podcast is produced by the MITRE Corporation with funding from the Cybersecurity and Infrastructure Security Agency.
Welcome to another episode of the Out of Bounds Read podcast. I'm your host, Steve Batista. Today's episode focuses on the recent introduction of hardware weaknesses into the CWE corpus. We have a series of interviews from different hardware specialists around the world about their perspectives on hardware security, CWE, and the state of cybersecurity at large. First up, I spoke with Jason Fung, Director of Offensive Security Research and Academic Research Engagement at Intel. Jason, why did you join up to help the 2021 CWE Most Important Hardware Weaknesses list?
Hey, thank you, Steve, for having me here. It is actually a little bit long story. So it started all the way back in 2014 at Intel. We actually kicked off this annual process to review hardware security issues found internally and try to build out some training materials to educate our hardware designers and validation teams and help them to prevent and detect these issues more effectively in our own product. And we go through that process a few years, and we collected some of these issues and we categorize them into these categories. And then we ask ourselves, well, yeah, we actually train our teams and now they're aware of this. But then we still have a problem about having more tools, more automation tools being available to allow them to apply so that they can detect, prevent these issues more autonomously. The other part is also about some of these issues are pretty much like widespread issue. And we wonder, are there any systemic mitigations that we can learn from and help address these problems? So when we look out and look at the ecosystem and ask around, people are not really aware of what we are talking about. And we thought, okay, perhaps we should actually share these issues more broadly with the ecosystem and the industry and academia and help them be more aware about these issues. And I'm sure we are not alone. And other companies also have a similar problem, but making it more available would enable all of us to be able to find better ways to automate our security assurance and finding systemic mitigations. So that's how we started this journey. And I still remember back in the days in summer 2019, we have this meeting with a few of our MITRE partners to bounce back the idea that what if we take the current CWE, which is software focused, and extend that into hardware domain. Do you see a value? And of course, the answer is positive. And by the time when we fast forward to February 2020, we actually release this CWE 4.0, which is the first time we have this hardware CWEs. So kind of it is a little bit long history about how I got involved. And of course, once you started this CWEs, it now has over like 100 or actually close to 100 entries. For newcomers, right, kind of figuring out how can I apply to it, it is a little bit overwhelming. So the natural step is let's figure out maybe zoom into the top 10 or the top 12 and help people to understand these are the most dangerous, most common, most important issues for them to first focus on. And that's the birth of this CWE most important hardware weaknesses.
I can see that you really need those automated tools. I have 2 Intel machines on my desk as I'm doing this podcast. So I have maybe 5 billion transistors sitting around on my desk at least. So yeah, I could see that, being able to explain this between other companies and having a methodology really would help with tools. What's a couple of the CVEs that are really helpful that are named that help you in using those tools?
Yeah, so for the CWEs that are pretty interesting, I think the access control, the common so-called like usual suspects that I call, right? Because when you actually create a really complex SoC chips, a lot of these resources are shared by different entities internally, and we classify them as trusted and trusted. Even for trusted, there are several layers of trustworthiness that you need to instill. So that you allow the good guys to be able to access important resources and kind of deter the bad guys, right? So access control definitely is very important to make that happen. And given we're talking about a SOC with like thousands or hundreds of thousands of signals and registers, how can you kind of bucket them into who can access what, right? Becomes very challenging. So we see often is there are certain registers that are misbucketed, and you may allow someone who is not trusted to be able to access it, and that creates problem. And when I talk about this thousands or hundreds of thousands of these like entities, right, some of them, a lot of them are not security related. They are just functional. So kind of sorting out which ones are security relevant and then making sure they are properly protected is a huge deal. And we see CWEs 1189 or 1260, they're basically talking about how you can provide proper access control to make these resources like registers and memory ranges to be well guarded.
That's interesting. So you've probably been at this for a long time. What's one of the couple items on the list that surprised you that are on the list? You know, if you could go back 10 years ago, what are some of the surprises that are there?
Right. Yeah, I have been working on this space for my last 17 years, so on security and hardware security. So this list is kind of ingrained in my brain, and I'm glad that you asked if I kind of roll back about 10 years ago. I think that makes a lot of sense. For some of these issues like side channels, physical attacks, right? These are the issues that we know they are there, right? We know it is important for the community. For example, especially for projects that actually are funded by the government, they care about a lot about how some of these devices could be exposed to adversaries in the field, and what if they acquire the physical possession of those devices? What bad things can they do? And there have been a lot of research in the past decade or two, or even maybe further back, on how can people harden these devices against attack. And we all focus on the physical possession of it, and a lot of the mitigations are being employed over there. But one thing that people haven't been thinking enough about is, at the same time, when we are hardening the physical possession, we actually also run software on top of these devices. And by opening up some of these APIs to the software to interact with the hardware, we may actually give them a little bit more privilege. And this is going to this CWE 1256, where we talk about the improper restriction of software interfaces to allow them to access the hardware features. And these hardware features actually give them the hooks to perform like an attacker, physically possessing the system. And they may be able to play around with the current, with the voltage, with the power state, and basically perform some simple physical attacks, even though the software are running on top and the attackers are controlling remotely. So I think that one is pretty fascinating.
Wow, I didn't know that there were some potential interfaces to adjust some of those basic physical properties from the software. That's fascinating. So
yeah, it makes sense when you think about today's operating system actually control a whole lot on the hardware and make the hardware to be more power efficient, or you can actually put a core to sleep, or you actually put all the cores to the highest frequency mode so that you can entertain these workloads like gaming, right? Like video processing. And if you don't have these kind of workload, you kind of put them into a low power state, right? So a lot of these so-called temperature sensing, power management, performance boost features actually are controlled by the system software, and because they actually know about the workload much better. And when you give away these really powerful control, but unfortunately, if the proper protections are not in place, then it becomes also a powerful tool for the attackers.
So you've already said that you use the hardware CWEs in communicating with other people where these weaknesses are for tool development. Are there any other ways that your team winds up using the CWEs?
Oh, yeah, indeed. So we actually look at CWE as a primer or taxonomy to help classify issues. So part of our learning here is that when we find issues internally, or when we learn from researchers externally about some product issues, we actually take time to understand the issues, root cause it, and apply CWEs to classify them, so that over time we have this collection of number of bugs in a number of buckets of CWEs, and that allows us to perform retrospective, learning about why these issues are there. Is it because the employees' trainings are insufficient? Is it because they don't have enough tools to use to address these issues? Is there something fundamentally, right, that we need to change the way we design our hardware so that we can actually minimize these issues or the impact of these issues, even if they got introduced by mistake? So we learn from this, and then we share the learning back to our internal teams to educate them. So that's one way we use the hardware CWEs. Another way is also we take this learning, and previously when we need to interact with folks from the outside, like the academics and the in the EDA industry, it is really hard to show them what we mean without giving them a concrete examples. And by having hardware CWEs, we now can point them to this CWE entry and help them to appreciate what do they need to take part in order to provide their innovations, address the issue. So CWE is definitely being used internally and also our external interactions and collaborations.
So do you have any good stories around the development of some of the CWE weaknesses at Intel? Anything interesting?
Yeah, I think from a development point of view, definitely, I don't know whether it is interesting, it may be frustrating, I would say, would be when we put together a few of these issues on the table, we look at it, okay, this is one way we can group them together. And then when you show it to other stakeholders, they say, oh, no, this is not my preferred way. Why not we group them in a different manner, right? So I think this is part of the process of classification, how to make this classification to be more meaningful to the audience and help them to relate to it better. And it is just like how you slice a pie, right, in different ways. And this is hard. And this is you won't get one answer. And that's why I'm really thankful for having MITRE working on this problem for so long, right? And you guys have this expertise about different views that you can provide to different users coming from different backgrounds. So there is no one way that everyone has to apply the same view, the same hierarchy. You allow people to actually mix and match different views based on their research background, based on their product background, or their focus is focusing on maybe, let's say, self-driving car or just a general purpose SoC, right? So they get to see their own view, which solve a lot of our problem that we encounter. Another maybe perhaps a funny story is before we even have the CWEs published externally, my team is actually working on research. That's why they also like publish paper from time to time, and they tell people about this is a problem that we need to address, and this is a solution, innovative solution to address them. So there is one time that we submitted a paper to a top tier conference about a problem that we see recurring internally. And one of the feedback coming back to us from the reviewers is saying, why do you think this is an industry problem? Who says so? And before we have hardware CWEs, they don't know us, right? It is a double blind process. So they don't know whether we are a student coming up with an idea or actually a company experiencing the idea. But now with hardware CWE, I can pinpoint to look at this particular entry in CWE. This makes to the top 12. It must be important. So I really appreciate having this top 12 list being announced.
Well, that's great. So that is a pro tip to all the people who are publishing papers. Include CWEs in them, and they'll get through the author review, correct?
Exactly.
If you had a magic wand, what would you like to see in the CWEs of hardware?
Yeah, I think there are two things I really want to see that happen. So having a really good, robust set of collaterals is the first step, but really changing the industry, making sure people can benefit from it is a huge deal, is what makes the whole effort worthwhile. Right now, we are still at the baby step of this process. We have the materials being available. I really hope more organizations would start using the hardware CWEs and also share their learnings. and their learnings will be valuable to contribute back to this community because, right, we have a number of companies and academics and government entities help shape this, and we are representing the product, the technologies that we are operating on. And I'm sure there are other industry partners who work on technologies that are not covered by today's special interest group members, that they can continue to add value to make this hardware squeeze to be more broad. So that definitely is one thing I really want to see. The second part is also about learnings about trends and challenges being faced by the industry. And I hope that by more people using hardware CWEs to tag their issues, their CVEs that affect their product, we now get a data-driven kind of set of trend that we can create. And we can be able to revisit this trend maybe every year and see, oh, okay, these are some of the issues that got increased over time, and maybe more actions needs to be taken along that line to prevent or help detection to be much easier. And hopefully over the next year, we will see the die down of some of these issues, and the rise probably will happen on something else, right? So by being able to look at the trend, we can actually invest as an ecosystem, as an industry, more in a more informed manner.
That's great. Is there anything else that you wanted to talk about, or?
No, I think this is awesome.
All right, great. Thanks. What a great conversation. Thank you.
Thank you. Take care. Bye-bye.
Next, I spoke with Jason Oberg, who co-founded his own hardware security startup. Okay, so the first general question I have for you is, what is your title?
So I'm Jason Oberg, and my title is co-founder and chief technology officer of Tortuga Logic.
Jason, why did you join up to help the 2021 CWE most important hardware weaknesses?
Thanks, Steve. Thanks for having me. So, we really saw the growth. We've been seeing the growth in hardware vulnerabilities over the last few years, and really we're excited to see an initiative focused on categorizing the common hardware weaknesses. When that originally came out in early 2020, and so we've been involved with this initiative for some time. And one of the first things that the industry wanted to see was, out of all the submissions within the CWE database, which are the most important? And so right when this discussion came up, I was very excited to participate and provide our insight into what we thought were the most important. And that's kind of really the start for how we got involved and where we are today.
When working on the list, what was the most surprising item that you found?
The most surprising one for me was actually CWE 1240, which is a use of a cryptographic primitive with a risky implementation. And the reason being is that cryptography is pretty well established into standardized algorithms that have been vetted by the cryptography community. And so it's actually surprising to me that people would still be using cryptography that is not vetted, that is custom, because there's so many established solutions out there that are vetted. So that was a surprising one to me, that that the industry saw that. Obviously this is an important weakness, but I think the fact that it was selected means that there's concern about it, meaning that people are still seeing this out in the wild. So that was surprising to me.
Yeah, that's really interesting. Being a software guy, I wouldn't think of rolling my own crypto. Not that I've been in computer security for a long time, but it's interesting that some of the hardware vendors did that. I guess they're trying to save cycles or something like that. Very interesting. What was your favorite weakness that was on the list that you said this is really important?
Yeah, my favorite weakness was CWE 1189, which is improper isolation of shared resources on a system on chip, primarily because fundamentally hardware is a very shared resource. You have multiple execution contexts, you have different privilege levels that are running. They're all sharing the same physical hardware. We saw some of the impact of that with Meltdown Inspector as it relates to speculation and so on. But really the fundamental issues that we see in hardware security, they're really rooted in these types of problems where you have shared resources between different privilege levels, different security contexts and so on. Like, for example, sharing cryptographic engines after you've completed a secure boot with user level software. These types of things are a root cause of a lot of issues. So I think that's a really good one to make the list, because that's a big issue that we see. It's a very broad weakness that covers a lot of areas that are the root cause of a lot of issues that we've seen.
So how do you use the hardware CWEs at this point?
So from our side, so a bit about Tortuga Logic. So we primarily provide software and products that can help detect security vulnerabilities in actual hardware designs. So we provide a lot of tooling and helping enable more of a comprehensive security program around how you can vet semiconductor designs for security weaknesses. And so we really use the CWEs as a driver for our products. So we have templates built based on CWEs for our Radix software tools, so someone can easily translate a CWE into inputs that you could insert into our Radix software tools, and then actually execute those on the real semiconductor, system on chip designs within the existing EDA type environments, the simulation emulation environments. And so really we use CWEs pretty extensively for a very important kind of, I'd say, metric for ensuring that your security program is actually covering all the applicable weaknesses for the particular design or project that they're working on. So it's really an input to our software and is really enabling a lot of the analysis that we do.
Are you starting to see that nomenclature is helping forge discussions about what needs to be done?
I do, yeah, because I think prior to the CWE release, and as obviously is prior to the most important release, everybody was kind of using their own terminology around what weaknesses they cared about and what they were looking for. So this introduction was very powerful because it enabled everybody to kind of have a level set discussion. So you can easily say, okay, this is related to, for example, as I mentioned earlier, CWE 1189. And you can talk about those types of issues in that context, rather than everybody kind of using different words and thinking they're talking about different things, but they're really talking about the same thing. So I think that was very helpful, definitely in that respect, to level the discussion across the industry.
So do you have any good stories around the CWE hardware weaknesses? Anything interesting that you can talk about that you've seen?
So obviously, I can't go into tremendous detail, but I would say that the reason I picked CWE 1189 is because we do see real instances of those types of issues when using our Radix products with customers. We're really looking at how information from different security domains, like different privilege levels, for example, how that information can be leaked across those domains, and really the underlying mechanism that happens is due to kind of shared hardware resources and so on, things not being properly cleared. And so we've really seen real hands-on leakages that are pretty significant, within that CWE 1189 type of use model. But I can't go into the specifics, but I think that we do see the CWEs being very useful for us communicating kind of the impact and potential problems with what we're finding.
Yeah, that's really interesting because it'll, at least for me, what I've seen is that there's CWE 1241 that talks about the use of predictive algorithms in random number generator. There's a recent news article in the last month dealing with true random number generators not creating enough entropy and failing and not reporting to the software, and the software not picking up on that failure, so that the random numbers were not really random. And I never thought at that level of detail, the interaction between the hardware and the software, that the hardware was using a true random number generator, but it would fail. And the software would be like, hey, I'm going to ignore the fail message. So it's really kind of interesting how all this stuff interacts.
Yeah, definitely. I mean, even if you relate that to CWE 1231, which is an improper prevention of lock bit modification. So like a TRNG, for example, as you referenced, it's a hardware resource that's taking as input like clock skew or something to create a random number, or some other entropy within the system, right? If that's not properly locked down after when you're executing user level software, and user level software can go and just modify configuration registers or whatever they may be for the TRNG, that will completely change the entropy and behavior of that hardware asset in when it's being used by privileged software and so on. That can have really negative impacts on the rest of the system that impact
not only
everything else.
Not only negative impacts, but really dramatic impacts that may be hard to see on the surface, right? Because you get random junk from a random number generator. Sometimes it's hard to know on the surface whether it's truly random.
Yeah, exactly.
So if you had a magic wand, what would you like to have CWE around hardware do?
Let's see. I would say, I think one of the things that that the community is working on that I think would be beneficial is to provide more concrete examples. The difference between software and hardware is that software is typically, you can describe examples with code snippets. You can say, here's a buffer overflow. This is what it means. Don't do that. Whereas hardware tends to be a bit more architectural. It's how things are kind of connected and implemented. It's less around a bug in, the Verilog or VHDL, the actual design languages. While there, obviously there is instances in which that's true. So I think having, it would be really nice if if I waved a magic wand that all of the CWs had very concrete examples tied to them. Because then I think that would help even more the industry understand and use them because they'll be able to very easily relate that example to something that they're dealing with, even if they don't understand the verbiage and so on. So I think that would be pretty impactful for the industry if that was available. And I know some of that's there, but I know there's a lot more work to be done by the community there.
So are you saying that maybe an undergrad or a graduate level class going over some of these CWEs and how they work would be really useful?
More specific. So I think that would be good. Just general education on it, I think, is good. But I was referring more to adding examples to the CWE entries themselves that are more hardware specific, because then I think it would help users of CWE more effectively apply them.
Next, I spoke with Paul Wortman, a cybersecurity research scientist at Wells Fargo. It's a pleasure to meet you.
Nice to meet you, Steve.
So why did you join up to help the 2021 CWE Most Important Hardware Weaknesses list?
So I ended up being a part of the effort in kind of a roundabout way. So I really started it more as part of some research I was doing for my PhD, looking into version 4.4 of the CWE and trying to compare how well or poorly, in my own opinion, the current state or version 4.4 of the CWE managed to map the existing hardware weaknesses and vulnerability landscape. And so it sort of started with that, where I spent a year and a couple versions of the CWE essentially just following everything that everything from the hardware design that was being put out. And so from there, along with some industry engagement I was starting to do with SAE's G32 group, and a whole bunch of emails back and forth with Alex Summers, I sort of fell into the CWE hardware SIG and kind of found myself helping out with this hardware weaknesses list in that respect.
Great. What was one of the most surprising items on the list for you?
I don't know if I would necessarily say that any of them are particularly surprising. I would say maybe, what is it? CWE, I have written down here the number, CWE 1189, which is the improper isolation of shared resources on system on a chip. And that's mainly just because I guess I would kind of see that as a bit of a software issue. I mean, I can see where the hardware problem comes in a scope there. But I don't know. I'm not as much surprised. In my previous life, I used to help run a black box penetration testing lab that was a joint effort between Comcast and the University of Connecticut. And so in that, we got a huge mix of embedded systems, so a lot of hardware, software. So a lot of the top list looks very familiar to me. There's maybe one or two that are a little more industry specific, such as the ones that deal with lock bit modification. But for the most part, I didn't find any necessarily all that surprising that they made it.
I think what's really interesting about CWE 1189 for me is the number of different isolation zones or areas that are now on a system on a chip, right? You kind of think of a chip sometimes as this monolithic, does one thing, but when you start looking at it, it does a lot of stuff.
Oh, absolutely. And even, I mean, I got some exposure to this from the days I was actively taking classes in grad school, because technically I'm still a student. But yeah, there was, I mean, some understanding of, all right, you've got a bit of a landscape here, and you've got some sort of isolated, and I'm sure I'm not using the terminology correctly as far as industry is concerned. But you've got some sort of isolated packages that exist there on the chip, and I can kind of say, all right, this maybe handles more of your wireless communication, and this handles more of your computation. But coming back to the CWE after not having looked at the fabrication of electronics in that same scale, yeah, it's definitely a lot more different. I was seeing a lot more terminology that I wasn't as familiar with. I mean, it makes sense, like definitely seeing fabric and built-in firewalls into this system on a chip design level was, I mean, I guess the word would be new for me, because I had not, I mean, at least learning about it, I don't think of it as, oh yeah, I need to see sort of this whole hardware space as a fabric, and you're going to have your own hardware level variants of a lot of these software concepts that are now cropping up in PCBs in a lot of these more sophisticated designs for hardware.
Do you have a favorite hardware CWE?
I don't know about favorite. I'm somewhat partial to the clock glitching one. Or I think there's only one so far. But yeah, so the CWE 1247, the improper protection against voltage and clock glitches, I guess I have a particular soft spot for, because a while back, and I don't remember exactly when this would have been, maybe half a decade or so, there was a Yukon team that I was a part of that I believe competed in a MITRE hardware challenge that we did rather well on, and it was because we figured out a solid clock glitching attack, had implemented some protection against it on our implemented team model. But that attack ended up being the clincher that I think helped us win first or second in that competition.
Yeah, that whole clock glitching and voltage glitching and stuff like that is very fascinating for me. So if you had a magic wand, what would you like to have the CWE hardware project kind of accomplish?
Well, so the answer that's going to get some eyes to roll, I'm sure, and I definitely spotted some of the jabs I was getting while the most important hardware weaknesses list was being put together, is I would really like there to be a better mapping between the CWE and the CVE, only because there is a CWSS score, and I would really like to make use of it. But it is a little difficult because the information that the CWSS scoring system requires, or at least as far as it is documented on the CWE website, is that a lot of the information is proprietary. And so you'll have this example that shows me how the numbers kind of work out, and I've got a good idea of how these different aspects kind of interact with each other. But there isn't a single solid example of, hey, here's this CWE that we're using as an example for performing the CWSS score. Here's how we came up with all of these values, and then here's the end result. And I get that it's a little bit of a special ask and an annoying request that I've been bugging all of you MITRE folks for at least 6 months, if not longer. And it's difficult because, again, because a lot of the information tends to be proprietary. Either we've got to find some sort of agreed upon standard for some of these. Costs are somewhat easy to figure out. Sorry, I realize I'm going on a bit of a rant here because my PhD research is doing risk evaluation for systems, and it's kind of started as embedded systems, and now the latest work I'm working on is trying to incorporate in some hardware and stuff. And so I get that some of the costs, like the specific costs for what impacts would be or what attacks might take for an individual to perform these actions is difficult to nail down. That I get. That's part of the reason that the CWSS score depends a lot on this proprietary information. And the answer I tend to get is we'll tailor it to your situation. But what I'd really love is to have one good, solid example using one of the CWEs existent in the database, and have an example that shows if you want to use the CWSS score for it, here's a CWE, here's the information that we're pulling out of our entries that we have for the CWE, what you can use from there. I'm sure there's some requirement that we're going to need like a matching CVE, probably mapped to that specific weakness before we can get real traction on that. But that is the short version of my rant of what I really would love to get out of the CWE one day.
Well, what's great is that it's a community project, so it just doesn't have to be MITRE that does that, right? So there are a lot of hardware vendors that could also join in on this, and we, if people are interested in this space, they could help out. So.
Oh, absolutely, and I know that there's work being done in that. Because again, myself doing kind of my own research and work, but I'm also helping the G32 work on a quantification table for hardware assurance. And that sort of is going to end up overlapping a lot of these same concerns. Is how do we, pie in the sky, how do we make a nice dynamic system for evaluating these weaknesses, threats, and vulnerabilities that exist out there, maintain that dynamic aspect, because as say like the CWE database gets updated or whatever other databases end up becoming part of the industrial and corporate lexicon, they're going to continue to grow and change. And I think the hardest issue that is going to take a while to tackle here is how do we grow dynamically with that? And I don't think that's necessarily on the shoulders of just MITRE or the CWE on its own. But it's definitely a problem that we've seen crop up across industry, across the various groups that I'm a part of and try to help and commit work towards, is that these aren't easy problems. And I think they're going to take a lot of group effort and checking information across various industries to really see where there is overlap and where there isn't.
Yeah, I always look at the analogy I use is you look at the early 1900s for industrial processes, and they were dirty and they were explosive and they had problems. We just hadn't figured out how to do it yet. And I think this thing we're working on is kind of similar to that. We really haven't done it before as a society, so we're kind of learning. And so until we figure this all out, there are going to be quote unquote accidents and mistakes and stuff like that. And that's all part of this process.
Of course, absolutely. And I agree. And one of the things that I guess is the balancing act that I guess is going to be more what we'll struggle with as this moves forward is how do you strike a good balance between getting these standards and this documentation out early enough that it can be useful, but not in such a way that we state that, okay, well, this is written in stone and that's just how it works, versus taking the time to really flesh some of these issues out, try, as contradictory as it sounds, to write some of this in stone as best as we can and have it so that these standards kind of grow as we grow and kind of piggybacking off your 1900 example, even with Miter's work with the CVE and CWE, because I had to write an entire related work section on it when I submitted this paper that's still in review. Even for this work you guys were doing, I mean, you started with the CVE, which really was just kind of a loose list of vulnerabilities that we wanted to use the same words to be able to describe. And then out of that, because some stuff didn't quite fit properly, you start getting CAPIC, you get the CWE. I mean, we've got the attack framework that exists now. And I think what we're seeing now, and I'm really heartened to see, is that despite the fact that these databases are focused towards different aspects of the larger issue of security and cybersecurity, they are really starting to overlap a lot more now. And at least in my opinion, what I'm seeing come out of a lot of these groups, and especially the ones that interact with MITRE, and I mean, specifically from my point of view, a lot of the growth for the CWE is that we're seeing this effort of, hey, how much can we really borrow and overlap from the CAPIC database to the CWE database? Hey, we've noticed that we don't really have a solid mapping right now between CVEs and CWEs, but I know you all are working on getting those hardware CVEs added to the database so that we can start doing a lot of this mapping work and try to have more of a framework ready so that when, I mean, not that the floodgates aren't already open, but when the floodgates really open, we'll have a better process together with it.
Yeah, I remember when CVE came out, it was such an amazing tool because before CVE came out, I would have to explain things in a paragraph. And when CVE came out, I could say, here's the number, go look it up. You can get more detail. But it was just so much easier to communicate those things, and it allowed the velocity to be so much faster. Yeah.
And that's what I think we're getting right now. I think that's more or less where we are now with the CWEs. We're kind of at that early CVE stage where we've got what we need to be able to say, look, these are the hardware problems we're seeing. We've got folks that are saying, you know, I don't see it this way, or, hey, you know, there's a whole host of other issues. Like I know from the G32 efforts that one of the big additions that are being pushed by SAE that they want in the CWE are these sort of supply chain weaknesses, which is a weird space. It's not necessarily hardware specific. It's not necessarily a weakness in the traditional sense, but they're definitely issues that are being tackled in that space. And so, at least in my opinion, they warrant being added to the database. Whether we find they're in the right place or whether we end up shuffling them around over the next few revisions in order to find exactly where they go, I think that's fine. In fact, one of the weirdest weaknesses that I'd submitted that, I mean, it's a weakness, but it takes you a while to get there, is one of the weaknesses that I submitted to the CWE is the idea that if you don't have a golden standard, that is the weakness. So it's not the documentation, but the lack of having it, because you require that golden standard later on for when you're examining whether or not hardware Trojans are existent within the hardware, whether or not the logic makes sense, whether or not all the functionality is present. And not having that documentation introduces the issue that you can no longer really check that these extra functions, if you were, are present or not. And so the vulnerability is only introduced by not having the documentation that you would normally use to check for these weaknesses, which isn't necessarily a weakness, but you can kind of see how, all right, it's the lack of having this thing that is the problem. And granted, it's a weird issue to argue about, and I'm sure you could argue that it belongs in the database as much as it doesn't. But I think it's good that we're having these weirder edge problems rather than, oh, hey, hardware is an issue, we really need a database for this.
Well, that's great. Well, this has really been a good conversation. Thank you very much.
Oh, my pleasure. Always fun to talk about hardware and the stuff I study.
Finally, I spoke with two folks at Riscure, Jasper von Woudenberg, CTO of Riscure North America and the author of the Hardware Hacking Handbook, and Nicole Fern, a senior security analyst at Riscure. Great to meet you.
Great to meet you, Steve.
So why did the two of you join up to help the 2021 CWE Most Important Hardware Weaknesses list?
So from my perspective, there's less public knowledge about hardware weaknesses and hardware security in general compared to software security, but we also see increasingly hardware being relied upon to implement the most critical security features in modern systems. So I really see the entire hardware CWE effort, including this top, N weaknesses list, as a way to promote the awareness of hardware security and encourage, knowledge sharing and collaboration across industry, academia, and government. And that's why I've joined this effort.
Yeah, I can add to that. So I think from my perspective, I've been doing hardware security for about 15 years now, and one of the hardest things in this field is just explaining what is good or what is bad about a particular solution, right? That's in the end, bottom line, what customer are asking. How good is it? And it's really hard to communicate about that if you don't have a shared language. And I think one of the things that the CWEs is trying to accomplish is to create these categories, create different weaknesses that you can now refer to as a common language. So that was one of the main reasons that I shouldn't say that Riscure is contributing to this, is to help the industry develop this language.
Well, Jasper, Nicole, what was the most surprising items that were added to the list from your point of view?
I guess I'll go first. So from my point of view, I found the fact that there were 2 CWEs related to lockbit protection on the list. I found that a bit surprising. Instead of there being kind of the CWE on more general access control mechanisms being on the list. But really, this is interesting to me because it indicates that this is a problem that has been seen many times by companies designing SOCs, and it's definitely plagued them quite a bit if such emphasis is placed on it.
Yeah, for me, I actually had no surprises. I looked through the top 10 list, and at each of them, I was like, yeah, I've seen that, I've seen that, I've seen that, I've seen that. So I think it's actually good to have not too many surprises in this list, because it sort of reflects industry reality, if you will.
What kind of surprises you with the evolving of this list? I know, Jasper, you've been doing this for 15 years. 10 years ago, what would you be surprised about that's on this list?
Well, there's one which I particularly like.
Okay.
And that is technically the CWE 1256, improper restriction of software interfaces to hardware features. But really, this is a bridge between two worlds that we hadn't seen 10 years ago, that of hardware weaknesses and software exploitability. So I always like to think about hardware attacks as kind of, there's 2 sides to it. There's attacks on hardware and there's attacks with hardware. So attacks with hardware is I'm connecting, an oscilloscope to hardware or a fault injection probe, and I'm trying to manipulate hardware. That's attacks with hardware. It's also an attack on hardware, right? I'm connecting it to a chip. But with this CWE category, we're adding attacks on hardware using software. And the reason why this is important is it changes the scale of these attacks on hardware, right? We were talking about, fault injection, a side channel analysis, and all these things 20 years ago. But now all of a sudden, they become remotely exploitable. If I'm able to run some code on your system remotely, and I can trigger any of these vulnerabilities, I can actually attack the hardware even while I'm not physically present at the hardware. So that's why for me, this CWE 1256 is sort of the most surprising, but also my favorite category in that sense.
Nicole, do you have a surprising one from an evolutionary point of view or a favorite?
So I actually picked the same CWE as my favorite one, but for all the reasons that Jasper stated, plus the fact that to me this CWE really highlights the tension between performance, usability, and flexibility on one hand that is considered during hardware design, and then security on the other hand, because a lot of these features that CWE highlights, some of these hardware features such as dynamic voltage and frequency scaling, all of that was added to increase performance, usability, and flexibility to hardware, but it wasn't considered from a security perspective. So that's why I find that CWE really interesting. And also over time, it's become more and more and more relevant as more features are added to hardware and more accessibility to those features are added to software.
Yeah, when I was on the team, I joked that was not a hardware weakness, but a software opportunity to talk in positive speak. So how do you two use the hardware CWEs?
Well, right now, I should say too little, but we're basically, like I mentioned, like the vulnerabilities that we've seen, they don't change, right? This list just identifies them. So I see definitely going forward an opportunity for us to start using this in our tools and in our services where we, analyze products to actually start using these CWEs to refer to. But yeah, to be honest, too little at this point. We're still very descriptive, and we still write down, hey, we found, I don't know, a corkscrew type vulnerability or something like that. But I would like to see that progress into, we found a CWE 1256.
And Nicole, do you have any other ways you use the hardware CWEs?
Yeah, for me, it's useful as a pulse check to gain insight into what sort of issues industry is concerned with, especially since hardware is very closed source and chip design houses don't necessarily publish, what weaknesses have been found in their designs openly. So it can be difficult to determine what are the broad classes of things that are of concern to industry versus especially what sort of things are focused on in academia. It's nice that the CWE kind of considers all of those different inputs together.
So do you have any good stories about any of these hardware weaknesses or, that you've come across in your career?
Want to go first, Nicole?
Actually, I don't have any good stories that I can publicly share, so I guess I'll turn it back to you.
That's the unfortunate part. You can't tell the stories until you're like in a retirement home, and then who knows, who cares. But
in my day,
we used to rub two bits together.
Exactly. Well, I do have one story actually from this morning. I was, preparing for the interview, and I typed into my favorite search engine, top 10 CWE hardware. I press enter, and I get a list of all the local hardware stores. So for me, this kind of highlighted we're not there yet in terms of like exposing to the rest of the world, like the hardware security issues in general. So I think, yeah, that's something that I'm hoping, over the next few years, we can make sure that I will actually get to the MITRE site next time that I type in this search query.
Yes, I tell my friends that I've been working on CWE and MITRE, and they're going, "What's wrong with your saw? I don't understand. your MITRE saw doesn't work right." So yeah. So if both of you had a magic wand, what would you like to see? How CWE and dealing with hardware and how it would progress.
All right. So if I had a magic wand, CWE, what it would do is it would make it so that the security nightmares and headaches experienced by one company can be learned from, by the entire industry and not repeated.
Yeah, nice. I think for me, along the same lines, right? hardware security, I mean, security problems in general and hardware security problems are no different, are, industry-wide. These things pop up everywhere, and we simply don't have enough people to manually go and figure out all these things, especially if we have these, inefficient ways of communicating about it or siloed information. So, I think my magic wand is the one of scalable solutions for security. So ideally we would get some tool where we would load the CWE list in, and it will spit out all the vulnerabilities you have, or even better, all the solutions to those vulnerabilities. So I know that magic wand does not yet exist, but we're working hard to at least go somewhat in that direction of being able, at scale, to identify and mitigate hardware issues.
Great. Are there any questions that I haven't asked that I should have, or anything you wanted to say?
Oh, that's a good question. Well, I think the main question that you should ask me is, Jasper, why is fault injection not in the top 10 list? And I'm not sure if I know that answer. So fault injection, I think, is a little bit lower on the list. But one of the things that I know from experience is that if your system isn't protected against these things, it's actually a really fairly easy attack. It looks fancy with wires and soldering irons and glitch devices, but there's enough publications out there to, for $50 to $100 of equipment, you can do a lot of damage to it. I mean, damage in the security sense to a chip, without reading specs or digging into all the details in data sheets or reverse engineering firmwares. It's sometimes just really as dumb as just glitching and glitching and glitching and just retrying it every time until you bypass some security check. So yeah, I think that's one that maybe I'm sounding bitter now. I'm not bitter of it not being in the top 10, but I think that's one that I think is important, just in the general sense.
So you really feel the fault injection can be accomplished with low cost hardware, but it's not in the list yet. But it's one of those interesting things.
Yeah, I think so. Yeah, low cost hardware and low knowledge as well. You don't need a lot of information into a chip to actually get attacks running.
Well, this has been a great conversation. Thank you both.
Thank you.
Yeah, thank you, Steve.
Well, that's all for the Out of Bounds Read podcast. Another one's enumerated. See you at the next podcast.
Thank you for listening to the Out of Bounds Read podcast, available on most podcast platforms and at cwe.miter.org. Stay up to date and connect with us on Twitter at CWE KPEC.